Good morning, here we are. It's the physics video lecture, physics 105B video lecture 17. We are working on gravity again. Although any homework problems or other things you want to have discussed, let me know in the email and then I'll discuss them like we did that homework problem last time. But yeah, we're back to gravity, the multipole expansion. And let's see what we can do today. I want to tie everything together, make sure it all makes sense. So let's start with the expansion. And we have enough to work with now. Multipole expansion. So we have V equals the exact expression dm prime magnitude r minus r prime. So you integrate over the prime vectors for some body here. Once again, there's our object, there's its center of mass, there's an r prime, there's an r, which is where we're observing it from, so to speak. And if we expand this thing as we've done, we have V of r is equal to minus gm over r, which is the magnitude of that vector, minus g, and then we have this interesting 1/2 ij qij xi xj. Those are the components of this vector r here, or this vector r here, over r to the 5th. So we've now actually calculated a couple of these, and I'll even put them down, and we'll just have this whole board up there. So first of all, we have, for the components of the quadrupole tensor, we have integral dm prime minus r prime squared delta ij plus xi. Left out that 3 the other day too, plus 3 xi prime xj prime. And the primes just indicate that we're integrating over the body. When you're actually doing the concrete example, you know, suit yourself. You don't have to prime them, you just have to get the right answer. And what examples did we have now? We have 2. We have for the, I'll just draw the small picture. We've got xy, we have the rod, minus L over 2 plus L over 2. And the second example, we have the ring. And so the ring we had x, y, and z, ring of mass m, radius r. So the q, I, j, in the case of the rod, make sure I get that, 6th and a 12th, ml squared over 6, ml squared over 6, and then minus ml squared over 12. Zeros everywhere else. This is a great thing if you have enough symmetry. Your off diagonals all vanish. Okay. And here, for the ring, the 2 first ones are the same. And what do we have there? Yeah. We have m radius squared over 2, m radius squared over 2, and minus m radius squared. So good, we have these 2 matrices to work with. And now we'll try to make some sense of all these things here. M squared over So the first thing you want to do is make sure that you understand how we get these. And the next thing, I'll just formulate homework. Not sure if I did this last time, so I'm just going to put it up here again. We want the quadrupole tensor of the uniform disk. And uniform disk, I'll just say capital M radius R. And it's almost this, well, the result is very similar to this, up to a factor of 2, I believe. And the calculation is similar as well. So let's go ahead and sketch that in here. In this case, X, Y, Z, we have a disk of radius R and mass M. Okay. Mass M radius R. So when you go ahead and do these integrals, you're going to have to use plane polar coordinates. And for the ring, I just did a d theta or d phi integral. You're also going to have to do a dr integral. But the answer that you get will be just like this, plus, plus, minus, and it'll maintain the same relations. This one will be twice as big as these two with a minus sign. And there's just a different factor in front, which is to say they're not just similar, but they're objects that have the same behavior in terms of gravitational attraction from a reasonably large distance, right? The distance from this object was supposed to be R prime over R for any of those R primes. It's supposed to be less than 1, substantially less than 1. Good, so you'll get that one as well. And what I want to do now is just write this thing out and expand it out carefully. So we want to expand out that double sum. And good, we'll do that first. I have a couple of things in store for us. If you want to expand out the double sum, what do we have? We have V of R equals minus GM over R. Fine. And of course, R is equal to root x1 squared plus x2 squared plus x3 squared. So we got minus GM over R. And now it's just bookkeeping, but I'm not going to expand them out for all the off diagonals. We'll just expand it out for the case where we just have the diagonals. So we have minus G times, in fact, I'll go ahead and do this. Okay. G over 2, and then we're going to have Q11 x1 squared over R to the 5th plus Q22 x2 squared R to the 5th. 3 x3 squared over R to the 5th. Okay, that's not so bad. Obviously, if we had the x1, x2, x1, x3, etc., it would be a lot greater, but in physics, we're typically looking for this sufficiently symmetrical object, so we don't have to make any apologies for this. For example, our oblate spheroid that we're so interested in astronomy, that will also have a diagonal quadrupole tensor, so nothing to worry about there. And now let's go ahead and take the example that we had this thing along the x-axis. So I'll just draw this. Here's the x-axis once again. This object here, v of x. Of course, that's going to simplify a lot because we're just looking along the x-axis. We have minus gm over x minus g over 2. We're only going to have the x1, which is our x. Okay. I'll go ahead and write x1. So we'll have q11 x1 squared over x1 to the 5th, since we're just along the x-axis. And q11 is ml squared over 6. ml squared over 6. And then that leaves us as 1 over x to the 3rd. Now here's the thing. This should be the result that you obtained with your expansion of that logarithm when we did the direct thing here in class. Right? When we evaluated this integral in class directly and expanded it out to 3rd order. Okay. But now you can take this expression too and do the y direction version and compare it to that, to the one you got with the direct calculation. And of course you're confident that you would have any direction whatsoever. So this was the comparison we were trying to make. Okay. So check this on the homework that you were doing, and when you do also check v of x2, it's going to be minus gm over x2. And what are we going to get here? We have a minus ml squared over 12. So minus g over 2, then we have minus g over 2 negative ml squared over 12. 1 over x2 cubed, and this was homework. Y was equal to the x2. That was that direction in this problem, that y direction. Right, so you're going to have a different sign and a different denominator there. Instead of 2 times 6 is 12, you're going to have 2 times 12 is 24. And again, what is the behavior that we're looking at? At a great distance, these objects look like a point mass. That's seen here as well, right? At the great distance, the objects look like a point mass. If you approach them closer, they have more structure. And you have this 1 over r cubed. Here you have just the 1 over r behavior. Okay, I want to do one more thing with this subject, and that is going to be with the ring. So I'll leave this material up here, and we're going to do the expansion explicitly with the ring and see what happens. Okay, see how our time is looking. Fantastic. So what we're going to do here, since we're doing the ring, we'll draw a larger picture. The ring M, R, and we'll put that here. So you got our X1, X2, X3. We can also call them X, Y, and Z if we want. And we've got the ring here. And the result I get in what I'm about to do is going to hold true for the disk just as well as the ring, the homework on the disk. So you've done it. You've done it. So let's go ahead and write out our V of R is equal to minus G M over R minus G over 2. And now our double sum. It's just the diagonal, so it's Q11 etc. So it will be mr squared over 2 x1 squared over r to the 5th plus mr squared over 2 x2 squared r to the 5th minus mr squared x3 squared over r to the 5th. We want to put this in a certain standard form, so we'll go ahead and pull out this gm over r minus g m I can pull out a lot, so gm r squared over 2 r to the 5th for starters. Okay. Gm r squared over 2 r to the 5th, so I end up with, actually, let's over 4. Let's go ahead and pull both of them down. 4 r to the 5th. So here's what we're going to do. We have x1 squared plus x2 squared. I'm going to add and subtract an x3 squared, so plus x3 squared minus, and since I have 2 times as many of these mr squareds over 2, it's going to be minus 3 x3 squared. Now, why am I doing this? It's because right here I have an r squared, and right here I have a minus 3 r cosine of theta. So now I have to explain. I'm going to go ahead and define, here's my point r out there. I'm going to define this angle of theta. So since I have this symmetry, r cos theta is my x3. Okay, so I was able to do that. So now I have r squared minus 3r squared cosine squared of theta. And now we can factor out that r squared. We're going to have equals minus gm over r. That's our point. That's their point source. And then we have minus gm r squared over 4. Then I have a 1 over r cubed. And I'm left with, so pull up the r squared, 1 minus 3 cosine squared theta. So yeah, this result is standard form for something else. This would be the corresponding term in the expansion with Legendre polynomials. And with axial symmetry, with spherical symmetry, we don't continue with Cartesian coordinates. Okay, we use different coordinate systems in order to do those kinds of expansions. Up to second order, this coordinate system is very useful to us, Cartesian. We did the quadrupole tensor. But this would be the next term in a series that goes on in terms of angles, r and theta. So yeah, it's nice to obtain that from what we did. Put a box around it. Of course, if you're using this formalism, you want to start taking derivatives in order to get the forces, then you're going to have to use the appropriate expressions for derivatives with respect to this coordinate system. But otherwise, it's very transparent, okay? Because you can see you've got the 1 over r cubed as your next term. See how your mass distribution comes in. And then you have this angular dependence. In particular, if theta is equal to pi over 2. Theta is equal to pi over 2, you just got the 1 there. And then this is your added term in that expansion. So I'm going to go right under here. Good. You want to go right underneath here. So, yeah, so it says this. Four. Theta equals pi over 2. I think orbits around the equator of an oblate spheroid, this would be V of R equals minus GM over R minus the GM 4 GMR squared over 4 1 over R cubed, and then cosine pi over 2 is 0. There would be more terms in that expansion. And if we were just doing, our Kepler problem type of thing, or if we were doing our apsidal angle calculations, we would have had an alpha over R plus a beta over R cubed. And depending upon the body, you're going to have some thing like this. Obviously for the oblate spheroid, it's not going to be mr squared over 4, but it's going to be something close to that. In fact, it'll just be another coefficient. We may come back and do those calculations because we have a little section on integration coming up when we do rigid body motion, and we can actually come back and do a calculation like this for an oblate spheroid. A little trickier, but you see what we've gained now. So if we had, I'll make our body pretty oblate, and we're doing an orbit around the equator, then this is that term that's going to play a role. It's no longer a perfect, Newtonian sphere with 1 over R potential, and there's your correction. And depending upon the body, you calculate that thing. This was, of course, for the ring. Yeah, so anything beyond this, I may just be wrapping it up and tying things together. Just put a little more commentary right here. So this coefficient beta depends on the actual mass distribution. And what I had been talking about, so in astronomy, we can measure the apsidal angle for nearly circular orbits, okay? We can measure the apsidal angle, C was equal to, just to remind you, we have that expression, root 3 plus U double prime of R0, R0, U prime of R0. Just to remind you, so suppose you can measure this thing really accurately for different R0s, for different circular or nearly circular orbits, then you can start to get this beta here, and based on the object that you're orbiting, you're not orbiting a ring, so you're not just going to say GMR squared over 4. You're orbiting this thing, and but you're going to have this part of the inertial tensor. And that can be extended. The higher order moments can be analyzed as well. But what we've studied is this here. So you measure this, you draw your conclusions about that, and those conclusions are right there, and you work your way back to what is actually going on in that body. So it's a pretty amazing technique. I just read an article about a satellite that's orbiting Jupiter, and they were saying they were getting many higher moments because their accuracy in position measurements are so phenomenally good. And from those higher moments, they're getting this and they're getting higher ones. They're able to infer something about the internal structure. Okay, so it's a great subject. I may call it right there for our gravity and this expansion chapter. Let's see where that'll put us. We could move on. Let's see if we are really done with this. So I'll just put as a note here, that's the orbit orbiting the equator, if we want to call it that, for one of these oblate bodies. That would be the same situation. Okay, good. So we will move on. No, actually, you know what? I have one more little calculation. Since we're on the subject of potentials and everything, this is going to return back to, I'll send it to the use of the integral theorems, in fact. Go ahead and do that, and then so this is wrapping up gravity. This is a good place to go. So we had the integral theorem. I'm going to right here recall Gauss's law. What was Gauss's law? We said integral G dot n hat d surface area, because that was a flux around surface bounding a volume V, is equal to minus 4 pi G m enclosed. And what else do we have? We have G is equal to negative gradient of V, right? We've just been working with the potential here. V is equal to minus G integral dn prime r minus r prime. Okay, so that's what we've been working with. What we're going to do is go ahead and work on this a little more. We've got minus 4 pi G integral density of R d volume, okay, over the volume. I'll use d3R, that's a volume element, okay. So we're going to apply the divergence theorem to this thing. Go ahead. Good. So let's go ahead and look at our top line there and conclude we have divergence of G over the volume, and we have plus 4 pi G rho d3r is equal to 0. Okay. Now, can we just conclude that this integrand here vanishes? Generally speaking, we cannot, but under these circumstances, since we say this is true for an arbitrary volume anywhere in this entire space, then since it's an argument similar to the fundamental theorem of the variational calculus that we did a while ago, we can conclude that the integrand vanishes. So therefore, because volume is arbitrary, we can conclude that the divergence of G plus 4 pi G rho, and rho is a function of R, right, is equal to 0. And then we can take G being minus the gradient of V, and then we can say divergence of minus the gradient of V plus 4 pi G rho of R is equal to 0. And we'll just bring the minus sign. We'll distribute this as follows. This gives us a del squared div grad V is equal to 4 pi G rho of R. So this is Poisson's equation, important differential equation. And then you learn techniques for solving it later on. But on the other hand, we do know the solution of it, right? That's right there. So Poisson's differential equation solved by this equation star, right? This expression right there. So that's another approach to gravitational theory. You solve this partial differential equation and obtain the potential. Okay. Good. So that was a nice little application. That ties actually a lot of stuff that we've done together. Good. So that will end our discussion of gravity for now. I'll just put up where we're headed next. And that is rigid body motion. So this is actually a major chapter, or even 2 chapters. Motion of the rigid body. Rigid body motion. And it's a major chapter. What I like to do is review what we did in Physics 4A, because typically people no longer remember what they did in Physics 4A. There are a lot of interesting phenomena. So the way we'll do it is first review the elementary theory, but it'll also give us a chance to calculate some things, some integrals, some centers of mass and so forth. So center of mass, axis of rotation, center of mass with axis of rotation, moment of inertia, and then torque, torque, kinetic energy, and dynamics. And so this elementary theory is basically fixed axis, so rotation about a fixed axis. Rotation about a fixed axis. So you can get out your physics 4A book and see what was all going on with rotation about a fixed axis and these concepts, because we'll go through these again, do some demos. It gets more interesting and much more technical when the rotation is not about a fixed axis. Axis is not fixed. And the stuff that we've been doing right now is going to come right into play, because just as an example, the moment of inertia down here turns into something called the inertial tensor, 3x3 matrix. So moment of inertia turns into 3x3 matrix. And you'll see why, and you'll see it's very related to our quadrupole tensor. So it's going to be good. It's going to build on things are going to build on each other. So when the axis is not fixed, then we have the actual technical theory of rigid body motion, precession of tops and things like that. Let's see. So that's where we're headed. So next time, I'm going to start with the center of mass. We'll do some calculations, center of mass, different coordinate systems, and work our way through some of this basic stuff. And then when we've seen the relevant phenomena, we'll talk about the non-fixed axis and the more technical aspects. So that's a good place for us to stop right now, and I'll see you next time.